Hey everybody, we've finally made it to the last section of our calculus journey. Today we're going to be looking at the area in between two polar curves. So we should just get started. Okay, so you're looking at that crop circle over there. I think you see that R. R means region. So we're going to be eventually doing something with that R. That's not part of the crop circle. So a crop circle, a crop formation, or a corn circle is a pattern created by flattening a crop, usually a cereal, so like wheat or rice or something like that. The term was first coined in the 80s by Colin Andrews. Crop circles have been described as falling within the range of the sort of thing done in hoaxes by Tanner Edis, professor of physics at Truman State University. Although obscure natural causes or alien origins of crop circles are suggested by fringe theorists, there is no scientific evidence for such explanations. And using for calculus of polar curves, can we find the area for the region marked with the R? The first thing we're going to do is make a mathematical model. Here's a mathematical model we're going to use. Looks pretty similar to what we had up there. We're going to use R1 equals 1, R2 equals 2 sine theta. 2 sine theta is going to be that red circle above the axis, and R equals 1, well, of course, that's going to be the blue circle. Notice that the region shaded above does not go all the way to the pole like we were talking about. So the things that we did with yesterday's methods, they're not going to really work here. Or are they? The intersection points, and this is going to be helpful to you, that's going to be at theta 1 equals pi over 6, theta 2 equals 5 pi over 6. That's a pretty simple solve. All you really need to do is set the two radii equal to each other. Eventually you'll come out with that 1/2 equals sine theta. And of course, when does sine theta equal 1/2? Pi over 6 and 5 pi over 6. So we also have the fact that this region in yellow is symmetric about the y-axis, which would mean that we can figure out the area of this first region and double that area. That will get us the entire thing, or the region of the area of the entire yellow section. I highly recommend you use symmetry. I always recommend you use symmetry. And they usually will make your integrals easier to compute. So here's a strategy. We're going to find the area of the region with the greatest radius and subtract it from the area with the least amount of radius. So coming back up here, we're going to go take this region and we're going to find this area right here. This is from pi over 6 and we're going to find this entire yellow region here. And that is just using the red curve as the radius. Once I've done that and I've found that area in yellow, I'm going to subtract from that this blue region. It's actually going to be looking green because yellow and blue make green. So we're going to subtract out this area right here. Then after we subtract those two, we're going to have the area of our desired region, or at least half of it, and then we're going to multiply by 2. So that's our general strategy. Not a whole lot more to it than that. The first region, the one that we did in yellow, that radius was 2 sine theta. So we're going to go from pi halves 2 sine theta, and we're going to subtract that from that 1 squared. And if we combine those two integrals, noting, of course, that we have the lower limit is the same, the upper limit is the same, So we can combine these two integrands together to make this super integrand down over here. So we're going to go and grab a calculator, and we're going to do all of this. Grab your calculator. No need for you to be in polar mode. Just chuck in those functions, the radius functions, into y1 and y2. Come over to the home screen. Set up your integral from pi over 6 to pi over 2, 1/2 radius 1 squared minus radius 2 squared. Push enter. Okay, and that is the area of half of our crop circle region. Region in our crop circle that we want is 2 times that result. And so what is 2 times 0.95661? I don't know. Computer, how much is 2 times 0.95661?
2 times 0.9566 is 1.9132.
Right. That's our region of the entire crop circle portion. Okay. Lastly, arc length. So let's remember this is going to work a lot the same way as it did last time. We've got the length, outer portion of any circumference would be the inner angle theta divided by 360 multiplied by 2 pi r. That's giving you a portion or a proportion of the circumference. Once we turn that into radians, it becomes theta over 2 pi multiplied by 2 pi r, which is just r theta. And similar to how we did it yesterday, theta is actually a delta theta. Adding it all up, and we get this arc length formula here. R d theta. Now, nothing, that's about as simple of a formula as you can get. With this limaçon here, if we want to find the circumference of that limaçon, you can just go ahead and utilize that formula. So it's just integral from 0 to 2 pi, 2 plus cosine theta d theta. And of course, since the upper half here is symmetric to the bottom half, I'm just going to go from 0 to pi and double it. Put those functions in your calculator. No need to be in polar mode yet again. Go to the home screen, quit and go home, as I like to say. Quit and go home. Here is the integrand, 0 to pi of the radius dx. And you come out with 6.28318. Write that down on your paper. And the circumference is 6.21318. Not bad, right? Pretty easy, actually. You're just integrating r. Now, of course, it could get more complicated. We could have different arcs that you need to add together. But really, the concept remains the same. Let's go over to our box. Okay. Take a minute here and pause, or I'll just talk through it. We've got the area formula again. It's the larger area using the outer radius minus the inner area using the smaller of the two radii. If you like, you can combine them into a single integrand, although it's not necessary. Arc length is just, of course, a to b of r. Let's take a look at the check your understanding. We're supposed to find the area between the limaçon and the circle. Take a second to analyze that, and you will see that this is actually symmetric about the x-axis. So I can go from 0 to 2 pi, and double it. I'm going to draw my own radii. So I'm going to start at the pole, and I'm going to go to the outer reaches of that region. So the outer reach of that region is right over here. That is radius 2, r equals 1. We're going to use that as our first radius. Two times the integral from 0 to 1/2. So I've got everything set up. That outer radius that we talked about, that was 1. Now the inner radius is going to be, well, let's draw that. I'm going to go ahead and put it here. That's going to be this, starting from the pole over to the first beginning of the region. That is the equation of the limacon, and the limacon is this one right over here, 1 minus cosine theta. So I think you've seen me put these in the calculator before. Grab your calculator and come back here. Just like before, there's no need for you to be in polar mode. Just put these in regular function mode. Use x for theta. You'll also notice that I put y1 equals 1 as the outer radius, and I put y2 as the inner radius. That'll just help me keep things straight once I go to the home screen and I enter in the equation. Notice we've got everything here. We're doubling the area from 0 to pi halves. 1/2 of radius 1 squared minus radius 2 squared. And if you push enter, you should have it. There it is, 1.2146. Come back to your paper and write that down. And that's everything. Okay, guys, that's it. That's the end of our calculus chapter 11. Hopefully you had as good a time as I did. Maybe you didn't, but I sure had a great time doing all of these. And don't forget to do your homework. I'll see you guys later.